Okay, there's a few things that I wanted to chat with you a little bit about inside of the computer and using Onyx and so forth. Specifically, if you're going to be reading in somebody's raw data and putting it into Onyx, I seem to have brought the wrong one up. There we go. This is how you'll have to do it. So the thing that you'll have to notice is that as opposed to, say, Amos or Caylus, where you would read in a correlation matrix and the standard deviations, and in the background, the computer makes a covariance matrix for you. Inside of Onyx, it requires you to submit the covariance matrix. So this is a tab delimited file, as you can see by the long lengths here, the long spaces here. You say covariance, and you put your variance covariance matrix in, mean, and you put those means in, sample size, and how big the sample is, and the observed variables and the names of the observed variables. So that's going to, in a research article or in your own explorations, you might be thinking of a correlation matrix, and you'll need to change it into a covariance matrix. And to rehearse that a little bit, this is what you might have. Here's all of our correlations. And down here are the standard deviations. So if you want to make this variance covariance matrix down here, you'll need to make a diagonal matrix of the standard deviations. I just copied and pasted it with zeros in the off diagonal. And downstairs here, look up here at the code. I'm multiplying L2 to S9 from here to here by the correlation matrix, C2 to J9, and then I'm multiplying that again by the diagonal matrix of the standard deviations, and that gives me the variances and covariances. So that's an example of the work that we had talked about earlier in matrix algebra, of taking a correlation matrix and making it a covariance matrix. Questions on that? I mean, you don't need to do this for the homework assignment, but I'm just showing you this step because that's how you would do this if you were going to make a data set that you could read into Onyx. All right. If, take a couple of days. I imagine on Wednesday you'll have questions for me of drawing the diagram or bringing some other software to bear on the model and fitting it and looking at the fit statistics, but we'll hopefully have more questions on Wednesday, unless there's any right now. All right. Without further ado, let's come back and look at our handout and talk a little bit about change and growth. So you can read the handout. We will be using the words change and growth very precisely in this chapter and throughout the rest of the course. And this is because change is a different thing than growth. Change in models, statistical models, represents a uniform jump or decrement in the scores of data over the course of time. So if at time 1, the mean of everybody is 10 and the variance is 1, and at time 2, the mean is 12 and the variance is still 1, we're going to say that scores have changed over the course of time. On the other hand, growth is a different thing. Growth means that as the average changes, variation also changes. So very frequently, if you're looking at longitudinal data, as the mean goes up, the observed variance in scores also increases. And we're going to say that is a pattern of growth. Similarly, decline, as scores go down, the variation in scores also tends to go down. And growth and decline have a mean that is associated with a change in variation. In order to talk about this and build some connections with what you've had in other classes, the first thing that we'll do is to talk about models of change. And this is because models of change are fundamental to repeated measures analysis of variance and many models of hierarchical linear modeling. The point here is for you to take a look at the path diagram that correspond to these models. Now, when you're looking at regular classwork in the general linear model that you've had, you'll encounter instructors who have a variety of explanations about what models are preferable. So, Doug Steinley is fond of saying, you should never do repeated measures in ANOVA. We should always just be doing Manova. And if you read other books like Maxwell and Delaney's analysis of variance book, they have a very nice little discussion about the trade-offs between repeated measures analysis of variance and Manova. To cut to the chase, before getting into the diagrams, if you have a small study, if you have relatively few numbers of individuals and repeated measurements, repeated measures analysis of variance is probably preferable to Manova. If, on the other hand, you have a large sample, many observations and multiple measurement occasions, it is probably preferable for you to run a Manova because the assumptions of repeated measures analysis of variance are unlikely to be met. In the middle, between repeated measures analysis of variance and Manova, all of these other little models that are models of growth kind of fit in terms of model parsimony. So that's the big picture. And let's step down now and take a look at simple models of change. Repeated measures comes in two flavors. We can talk about the repeated measures null hypothesis of no change over the course of time, and the alternate hypothesis that there is change happening over the course of time. And here are the two path diagrams for the null model. By the tracing rules, you can see that these two models are going to be the same. Let's deal with the first one on top. In repeated measures analysis of variance with equal intercepts, I'm going to be saying there's a latent variable out here. It has a variance. And downstairs, all of the manifest variables have an error variance, and those error variances are the same over the course of time. The assumption that, so in terms of the language that we've had so far in the class, this is a random intercept model, or equivalently, I could say the variance here is 1, and each of these loadings is the same, because that model would also fit the data just as well, the tau equivalent model. If we were to talk a little bit about measurement models, this model says that there's a strict measurement invariance property, and that's nothing more than saying that the loadings here are 1 over the course of time, and the error variance are the same. So if by the tracing rules we calculate the variance of T1, it's going to be 1 by 1331 times 1 plus 165.64. And those are going to be the same variances for each of the variables. Take a look also at what this diagram says about the covariance between measurement occasions. It's going to be 1 times 1331 times 1. And that covariance is going to be the same regardless of which pairs of variables you pick. This statement about equal loadings or loadings fixed to 1 and equal error variances has a fancy word in statistics. It's called the assumption of compound symmetry. Another way I can draw this same model is to say that the latent variable has a mean and the intercepts are all 0. Because by the tracing rules, you can see that 1316 times 1 is going to give me the same predicted mean of the manifest variable as I did having no mean for the random intercept variable and equal intercepts over the course of time. Why am I bothering showing you two equivalent diagrams? Well, one, for education value, it's going to show you some practice with the tracing rules. And the second reason is that in statistics, we specify these various models slightly differently to produce other models that are conceptually useful to us. So is this working? Now, I was playing around with the WISC data set, 4 times of measurement. And if you fit this model, the null model fits really poorly. And when I then come back and free all of these intercepts to be different, that model also does not fit very well, but it's a big improvement over the null model. So the chi-square difference test between a null model where these intercepts are the same and an alternate model where the intercepts are different is 1,520 with 3 degrees of freedom. Why do I have 3 degrees of freedom? Well, I have 1 parameter down here and 4 parameters down here when I have the alternate model. It's still a poorly fitting structural model though, when I let those intercepts be different. So it's not entirely satisfying. Here are 2 models now that we'll consider that are alternate ways to specify the alternate model. In this first model, all of these intercepts are different. And in the second model, look what happens. I'm going to have this mean over here with 1s, and I'm going to freely estimate 3 intercepts down here. So it's Monday morning, and everyone's really quiet. So I'm going to ask a question, and I'm going to wait until I have an answer. What does this diagram down here say about the mean of time 1 using the tracing rules? What will that be?
Will be alpha times 1.
Yes, exactly. Good for you, Andreas. Okay, and now we need another brave soul. You did that. All right, what does this diagram say the mean at time 2 is?
Is it alpha times 1 plus the other arrow coming to?
17.20.
Yes.
So this 17.20 represents what? How many points? you can kind of cheat. Yeah, go ahead.
Yeah, we can go ahead.
Well, I mean, we can kind of cheat. We can come up here and look at the fact that up here, the mean at time 2 is 35.98. So this number down here is 18.78, the mean at time 1, plus this number.
Yes.
Okay. So what's going on here? When you took analysis of variance, we talked about a priori contrasts. So the test here, I'm sorry, this is, I'll need to move these over a little bit. This T2 is 7. So 16 plus 7 is 27. I should move this over to this by this arrow, and this is by this arrow, and this is by this arrow. But having said that, so the statistical significance of this path is going to answer the question, is time 2 bigger than time 1? The statistical significance of this one up here is answering only the question, is this intercept bigger than 0? So maybe, in your research, you might be interested in asking the question, is there some individual growth over the course of time relative to time 1? Sorry, growth is the wrong word, change. And it helps to think about this as a scatter plot. So if we come down here and we calculate the...
Really quickly, sorry to interrupt, but
Oh no, please, let's do it slowly.
Before we go on, just to clarify, maybe in the original and the null model or in the models up above, if we could go back up there. I think I'm a little bit confused as to what like the role of time in this. Is it a latent, is it a response, or is it a predictor? How are we treating, how can we tell what each of these things in the diagram is representing?
Well, in the diagram, T1, T2, T3, and T4 are the manifest variable scores. So each record in my data set, I've got 4 variables, whisk time 1, whisk time 2, whisk time 3, whisk time 4. And my questions here in this model is I'm going to say the mean at all 4 measurement occasions is the same number. Dear SEM program, come on out and estimate for me the best guess for what this mean is. So this is kind of, well, this is the grand mean taken over time. Does that work?
So in here, time is the response variable.
Mm-hmm. Yeah. So it's the person's whisk score, the child's whisk score in, it was kindergarten, 1st grade, 2nd grade, and 3rd grade.
Okay, thank you.
Okay, that's great. More? I just have to be more patient. Pat King, who was my advisor at Iowa and just retired recently, said, don't be in a hurry to answer questions in class. If you ask a question, you sometimes need to wait up to 2 minutes, which to me feels excruciating and awkward, but okay. So this is all there is, folks, to repeated measures analysis of variance. So if we come downstairs here, because the error variances are the same, if I take plus and minus 2.58 standard deviations around this, in the alternate model, this is a scatter plot of what I expect the means and variances to look like over the course of time. So this visually is a statement about that this statistical model is only looking at change. And the point that's made here is both of these models are poor because it's probably the case that variation in scores changes over the course of time. So if you are a believer in the repeated measures analysis of variance model, we generally do not believe the F statistic that comes out of that and the p-value. We employ two common adjustments to account for the fact that the assumption of compound symmetry is not met in the data. The Wynne-Felt correction, H-U-Y-N-H, Felt, F-E-L-D-T. Leonard recently died. I had him in a number of classes when I was at the University of Iowa. And the other one is the Geyser-Greenhouse correction. So those two models say, okay, we're doing repeated measures analysis of variance. We're going to assume that compound symmetry exists. It is probably the case that the p-value is wrong. So here's a correction to the p-value. If you are playing with these data in analysis of variance software, there's two ways to think about your data. And the reason it's a good idea to take a moment and think about this is we can either think about our data in wide format or in tall format. Sometimes people use slightly different words for this, but what we've been doing here has been to analyze our data in what is called wide format. Each record in the data set corresponds to one individual in my study, and I have 4 variables. The other way to think about the data is in tall format. So what I'm going to do in tall format is to have only one variable in the model. That's my dependent variable, and an ID variable indicating who this is, and a time variable that will indicate what measurement occasion it is. So let's go slowly through that for a bit. Now, why do you care about wide versus tall data? Makes my head hurt a little bit. Well, wide data lets you look at a greater variety of growth curve models than tall data. Tall data is a way of analyzing data in hierarchical linear models. We need to make a few restrictive assumptions when we have tall data. One of the nice talking points about tall data is I might have a longitudinal data set where the measurement occasions on the individuals are different across the participants in the study. So, I'm trying to do my best to speak slowly here. Well, let me get rid of that so we have a little bit larger screen. If you were playing with SAS or even SPSS, this is a way that you might specify the data. ProcGLM, call up the software, list the individual variables and manifest variables in your study, T1, T2, T3, T4 is what these are. And then you would say, oh, repeated time. And what that's going to do is to tell the computer program, all of these things to the left of the equal sign, those are different values of time. So when you're playing with this, you're going to get the following printout out. And it's helpful to take a look at that. It's going to give you an F statistic and not a chi-square statistic. It's going to give you this F statistic because analysis of variance has a closed form. It's not giving you a likelihood function. Downstairs here, we have error. This is the sum of squares error. And this 13.88, oh, that's kind of a familiar number. That's going to give us the variance, the estimated error variance in the data. So 165.64 is the square of this. All right. In tall format, we're going to take our data set, and as I mentioned before, we're going to make a single dependent variable and a time variable. And I can analyze that data here by saying now proc GLM, class, time, and subject number is an ID number that tells me what participant I have. And the model statement is going to be, here's my dependent variable, here's time, and here's the subject number. And downstairs, what I'm going to have in tall format is the following numbers. It's going to tell me this proportion of variance, this F statistic, is going to answer the question, are some people different than others? And upstairs, here's my time test with 3 degrees of freedom to test for the null against the null hypothesis that time is the same over the course of time. You're going to get the same numbers out of both of these statistics. 2,231, 2,231 ought to be down. I'm sorry, what am I looking at? Well, that's the time main effect. 2,231. So, they're going to give you the same number. The mean square error of 13.88 is similar to that 13.81 that we got in repeated measures SEM above. Well, how come you didn't get exactly the same number for the mean square error across the two of them? Well, the reason that you did it is SEM is based on all 204 individuals, and it only takes n minus 1 out as opposed to n minus k minus 1. Sometimes people, rather than using GLM, will use proc mix. They'll use an HLM piece of software. Well, if you're doing HLM in tall format, it's just proc mixed. Here's my data tall. And just as with GLM, here are the class variables, the ID number, and the time variable. And the model is this. You can then put in estimate statements that will compare time 1 to time 2, 1 to 3, and 2 to 4. And that's going to correspond to exactly the numbers that you get up here. And out of proc mixed, or out of any HLM software that you have, notice that you're going to get an estimated correlation matrix, covariance matrix for the subject effect. Well, what are these numbers? Well, these numbers represent compound symmetry. That is, this is the estimated variance of time 1, time 2, time 3, time 4, and the covariances are all the same number. These numbers are nothing more than what we saw above. When we're taking the variance, 51.26, plus the error variance downstairs, 13.81. So all that good old proc mixed is doing is giving you the same numbers here as you would get for the tracing rules. This is a variance covariance matrix. If I wanted, I can then take a look at what these are in correlations. In other words, if I pre and post multiply this matrix by a diagonal matrix of the square roots, that's going to give me the following predicted correlation matrix under compound symmetry. So compound symmetry is saying that 0.79 is the predicted correlation. This is the intraclass correlation coefficient under compound symmetry. And then downstairs, we have variance estimates for the people. In other words, people differ from each other with a variance of 51.52. And downstairs, here is 13.88. That's my estimated error variance associated with each manifest variable. And downstairs, I have a chi-square and a likelihood with 1 degree of freedom against the null model of no subject effects, and here's my time effects. So my point for bringing this up is there's one structural equation model that underlies everything you've had so far. When you took GLM classes, it was the repeated statement. When you're taking an HLM class, you're doing the same thing, but you're looking at it in tall format. And when you're looking at mixed modeling, this tall format, expresses itself as the same set of variances and covariances. So all of these models are models of change. And that's my point, that if you're going to criticize when you are writing an article, say in developmental psychology, very often researchers will say, well, if you have multiple observations, oh, well, and insert your favorite bias here, you get old people, say my age or older, who will say things like, well, when I was in graduate school, we did repeated measures of ANOVA. Back in the day when small data sets were more typical and computational power wasn't that great, and it's just habit. Or you'll get people who say, oh, I just attended a professional conference, or I just read an article that was the leading article in my area, and they did mixed modeling, or they did hierarchical linear modeling. And therefore, in your paper, you should as well. Well, my point is, in all of these cases, even if the models are elegant, these are all models of change. They are not models of growth. Okay, are there any reactions to this?
One question.
Yeah.
So if the variance, if we don't have compound symmetry and the variance from time 1 to time 2 is different than the variance from time 1 to time 3, is that where we're going with this?
There's a couple of places we can go with it. I mean, I realize that as I've written this out, it's maybe a lot to process, especially if you've not maybe yet had a class in HLM. But I like your instincts that one way to free the model, thinking as a structural equation person, is to say, well, maybe this latent variable up here is okay, but downstairs, measurement error changes over the course of time. If you're an educational researcher, for example, measurement error seems to be more of a factor with younger children. Kindergartners have an awful lot of performance variation from one measurement occasion to the next. So maybe you want to relax that. Or secondly, if you're looking at a geriatric population, as I'm rapidly advancing to, those people tend to have good or bad days. And so error variances with more elderly people may be larger than for younger people. Well, one thing you think about then is, hey, maybe I just want to say these error variances are different numbers. And if you'd like, but I want to keep that tau equivalent upstairs there. And if that's the case, then you are doing Kesselman's non-parametric repeated measures analysis of variance. It is still a model of change in the latent variable, but it's a model that allows there to be different error variances, more and more variability over the course of time. But the reason that error variances are changing is entirely idiosyncratic to that measurement occasion. In other words, there's no evidence that there are different trajectories of change in the data that we would call growth, or systematic inter-individual differences in intra-individual change. In order to have a model that looks at growth, I'm going to have to adopt some other latent variable here than the tau equivalent or fixing all the loadings to one model. And those are models of growth.
I see that answers my question.
Yeah, okay. Anything else, folks?
So, sorry, one more question to follow up. To know that we need to like let that variance like range in one time point. So we need to let it be a little bit different. How do we know that we need to do that? Is it just by looking at the variances in each time point and just knowing that they're different? Or is there some other indicator?
Well, the frustrating thing that people in statistics will say is, it depends. Well, so what does it depend on? So if it's the case that you have a very small sample, say 20 observations, repeated measures analysis of variance may be all that you can do with the data, because you just don't have the numbers to have a really complex measurement model. So with only 24 observations, for example, it's highly unlikely that I can fit a model where lots of loadings are free and the error variances are all free, because I'll start consuming all of the elements of my variance covariance matrix. And if that's the case, then all we can do is repeated measures ANOVA and employ the Geyser greenhouse or Limfeld corrections and say, well, that's all I could do. If, on the other hand, though, you have slightly more observations, well, yes, you're right. You can look at the data, and if, let's come downstairs and see some numbers. If you start seeing that, I'm just using this for didactic purposes. If you start seeing that the variances are changing over the course of time, but your covariances are kind of sort of in the same ballpark, then maybe you, as a structural equation model, you come up and say, well, hey, I'm going to free these error variances and compare the null and the alternate model under the assumption that the error variances are different. So you can specify the entire question as a structural equation model and calculate the chi-square difference and say to a reviewer or an editor, the reason I'm doing this is because error variances appear to be different over the course of time. Just to talk about Manova, which happens later on in the class, under Manova, your structural equation model is just going to be all of the variances and covariances freely estimated, and there's no latent variable involved. And I simply compare a model in which all of the intercepts are the same with a model that says all of the intercepts are different. So when I say all of the intercepts are different and all of the variances and covariances here are estimated and there's no latent variable involved, I have a completely saturated model with 0 degrees of freedom. And when I test the hypothesis that all of the intercepts are the same, well, that's going to give me a 3 degree of freedom test between the null model and this alternate model where all those means are different. But the question of variation at the individual level being accompanied by changes in mean is a growth model. So that's the big picture. That's why I'm comfortable taking a while to talk about it. So, yeah. Or is someone just breathing? Yes?
I was just wondering, like, so if I could you run like 2 different models, one with equal variance and the one with unequal variance, and then run an ANOVA between, like, to figure out which one is the better?
You can do that, right? I mean,
Okay.
you would do it as a chi-square, as a structural equation model. I could say all of these are the same, all of them are different, and the chi-square difference there would tell you, is the assumption that these error variances are the same going to be justified? Now the deal is, if so far you're doing repeated measures analysis of variance and you run that structural equation model, it's good for you because you're using structural equation modeling to show that one aspect of the compound symmetry model is not justified. The response from an editor or somebody, who does repeated measures ANOVA is, that's fine. You are proving that some adjustment to the p-value for an F statistic is needed. Therefore, if you're going to stick with a model of change as underlying the data, you should employ the Geyser-Greenhouse or Winfield corrections to the p-value to adjust for the fact that compound symmetry is not met.
That makes sense. Thank you.
Yeah. Mm-hmm. So I have just a few seconds, but in terms of showing you a path diagram to start off this discussion, growth has a mean for a latent variable in which the factor loadings are different. So the simplest example is the factor mean model first proposed by, well, actually somebody back in the 60s proposed it, but currently we think about Jack McArdle and Daniel Epstein proposing this in the Journal of Child Development. Look what's going on from a path diagram perspective. The error variances are free, and I have a factor mean here, and the loadings are free. So now the loadings, the variance of each manifest variable is going to be 408 times 1 times 408. And at a later measurement occasion, 10.11 times 1 times 10.11. The predicted variance of the manifest variable changes over the course of time. And up here, the factor mean is going to predict different means across time. So 4.67 times 408 is my predicted mean for time 1. 467 times 572 is my predicted mean for time 2. So these loadings here are doing, as it were, double duty. They are expressing variation, variance, and covariance that varies over the course of time. And these four numbers down here are also telling me how the mean level is changing. And we'll come back and talk about it some more, but what I want you to take home is, look how this curve differs from what we had with repeated measures analysis of variance. As the mean increases over the course of measurement occasions, variation in scores also increases. So this is why the factor mean model is a growth model and not a change model. And this is where we'll start on Wednesday. I'm going to put a pin in it here and take any